Alrighty. So number one, define acceleration verbally and mathematically. So you would say something like acceleration is. Anyone want to jump out there? Rate of change of velocity. That's what you got. How fast the speed or how fast the velocity changes. And mathematically, they want the formula. So they want something like A equals delta V over delta T. And remember, the delta means change. What type of quantity acceleration? It is a vector. What is deceleration? A word that I tend not to use, but it would be negative acceleration, right? I tend not to say deceleration because it could mean slowing. Deceleration tends to mean slowing down, but negative acceleration doesn't necessarily mean slowing down, does it? Because if something's already moving negatively, and the acceleration is negative, then it's actually speeding up. So I tend not to say deceleration. Number two, a certain car is accelerating at 5 kilometers per hour per second. Explain what's happening to the motion of the car. So you should have something like the speed of the car or the velocity of the car is increasing by 5 kilometers per hour every second, which isn't particularly fast. Give an example of a moving object that has a velocity vector, acceleration vector in the same direction, and one that has it in opposite direction. And I was working with Blaine, I can't remember the other day. I was talking about that yesterday. So if the velocity and acceleration are in the same direction, then that means the object is doing what? If velocity and acceleration are in the same direction, it is speeding up. So it would be like a car speeding up from a red light or a stop sign. And if those vectors are in opposite directions, velocity and acceleration, then that means the thing is slowing down. So a car coming to a stop at a red light. That's all they're getting at there. Number four, can an object be moving at a constant speed and accelerating? And I gave you an example of this yesterday, so the answer is yes. Can you give me an example, Kayla? Constant speed and accelerating? Something that goes around the corner, right? The old on cruise at the St. Rose corner example. Right? Constant speed, changing direction. And if you're going around a curve, well, we'll get into that when we get into circular motion, which direction the acceleration is. I'll just sort of throw that question out there and answer it in about 4 months. What will be the shape of a speed versus time graph for an object in free fall? Speed versus time. So speed, no direction, so positive, or no sign, I guess. And in free fall, so it's going to be constant speed or speeding up or slowing down. Martin jumps out of an airplane. He falls at a constant speed. He'd be accelerating, right? Until a certain point. What's that certain point called? Good point. I was talking about terminal velocity, but you're not wrong. So if the speed is increasing, then what would it be like? Flat? Slanting up? Would it be straight line like that, Tanner, or would it be curved like this?
Yes.
Austin, what do you think? Not sure. Remember, this is a velocity time graph, and this ties into good what we're doing today because we're going to sort of look at more of these. Okay? Actually, this is right here because this is a velocity time graph, and in fact, the acceleration, the slope of that would actually be minus 9.8, right? Remember, the slope of the velocity time graph is acceleration. So it would be like that, Tanner. You're right. For the first little while, and then that sort of wind resistance and terminal velocity would sort of start to kick in, and then what would happen? Go flat, right? So you're right, Pauline. It would curve eventually as sort of the terminal velocity kicks in, right? As air resistance kicks in. In fact, that kicks in right away, right? You've got something really light, something like this, right? If I drop that, well, it falls at a terminal velocity almost instantaneously. Something like Martin jumping out of a plane would take a little while. Okay, number 7. What's the relationship between speed and velocity? Well, velocity is simply speed with a direction. This is all kind of supposed to be review. Answer the following by referring to figure 3.5. So that is, oh, you have to go back a couple, right? The second page. So that's the graph that looks like this. And this is a position time graph. And the question is, over which interval did the object have its greatest velocity? So how do you find velocity from a position time graph? You're looking at the slope. So where is it the steepest? Sort of in there, right? So if you had to describe that interval, what would you describe it as? C to D, it looks like, yes. Interesting choice of letters. I don't know why they use C and D. Over which interval was the object's velocity decreasing? So the velocity is decreasing where the slope is getting flatter. So it looks like that area there, which I guess you could describe as, I guess, after D, or 6 to 10. And when is it increasing? Well, that would be this part here, right? Increasing, the slope is increasing. So I guess you'd say that's probably like, I guess, really, it's 0 to 6, isn't it? Right? It keeps getting steeper all the way from 0 to 6. Okay, last one. We'll move on. Sketch a graph of motion, distance as a function of time that would correspond to the following bicycle trip. You start your bicycle from rest, increase your speed until you reach a comfortable traveling speed. You continue with this speed for a few minutes by completing your trip by slowing down uniformly to a stop. So again, we're talking distance or position versus time. And we're going to start from rest and increase in speed. So we're going to be curving up, and then you reach a comfortable speed. That's probably too steep. And then slow down. Remember doing that on the exam? You guys will, that were just in grade 11, right? Okay. So we're going to spend the rest of this day talking more about graphs. To be honest, none of it sort of carries into a whole lot into grade 12, but it's a good way to sort of bring back some of those ideas, talk about velocity and acceleration to sort of get you going before I get into the new stuff. So, I have two. I have a position time. Oh, you can have that as well. What say you play? Oh, yeah? All right. You remember this? Some of you will, probably more so, because it's new. Some of you it's been a while. But this is kind of important. This is everything you need to know about position time and velocity time graphs. And you will remember that it's actually supposed to be sort of like this kind, right? Like a big page. So notice that, oh, this is actually the old version. Okay, anyway. So the right-hand side is position time. No, I've got that wrong. The left-hand side is position time, and the right-hand side is velocity time. So when you flip it over, that should be the same. And on the new version, it's labeled. But yours guys isn't. So let's just label that. So the left-hand side, at the top here, write position time. And on the right-hand column, put velocity time. And if you want to draw a line down the middle to sort of separate them, some people like that, sort of make it more visual. Okay, so what I'm going to do is I'm going to run down the position time column and just give you a quick review of this. So, again, down the left-hand side, if you have a position time graph and you are asked to find displacement, and I think I'll put some graphical little pictures to go with this, in fact. If you have a position time graph, sometimes called a DT graph or PT graph, and you're looking for displacement, how do you do it? You simply read the points off the graph and subtract, right? It's a position time graph. if you're asked to find average velocity and it's a straight line graph, what do? Number 2, straight line graph, you find the slope, and you should all remember how to find slope. Do I need to remind you of that? y2 minus y1 all over x2 minus x1. Right? I'm hoping you've used that in math at some point. If it's a curved line graph and you're asked to find average velocity, what do? Right? You find the slope between those 2 points. If it's curved, that's average velocity, average over an interval. And number 3, and if you want to draw these little pictures beside them there, that's probably a good idea. Should I slow down for a second? Okay, so number 3, if you're asked to find instantaneous velocity, what does that mean, instantaneous velocity? It's how fast an object is going at that moment, whereas average is over a interval, a period. Could be a really short period. Okay, so if it's a straight line graph and you're asked to find instantaneous velocity at a single point, can you find slope with a single point? You cannot, but because it's straight, you simply pick 2 points, and the instantaneous one could be one of them if you want. Pick 2 points, and again, find the slope. That's A. If it's a curved line graph, how do you find instantaneous velocity? Who remembers? What kind of line, Connor? Tangent line. Correct. Right? Tangent line. And remember that your tangent line might be slightly different than your neighbor's or mine. All good? Give me the nod of agreement. Okay, flip it over. If you've got a position time graph and you're asked to find average acceleration, the answer is can't be done. Okay, the only way to get acceleration is from a velocity time graph. So average acceleration, instantaneous acceleration can't be done from the graph, or not in one step anyways. You could create a new graph and do that. So the answer is can't be done. Okay, back to the front. Velocity time graphs. This is position time, velocity time graph. So if you've got a velocity time graph and you're asked to find displacement, how do you do it? It is the area. Remember doing that? Finding area. What happens if it's below? Yeah, and do you find the area below? No, you find the area between the graph and the axis. Right? They call it the time coordinate there, the axis. Remember doing that? It's a long time ago for some of you. Way back first semester grade 11. A year and a half ago. If you are asked to find from a velocity time graph number 2 average velocity, the only way to do it is with the formula v bar equals d over t. And how do you find the d? The displacement is the area from the number 1, right? So you got to find the area first before you can find the average velocity. Where d is calculated as shown in number 1. Number 3, instantaneous velocity. V-inst is read directly off the VT graph. That's easy. Whether it's curved or straight, it doesn't matter. You simply read it off the graph. How come? Because it's a velocity graph, right? If you want to know velocity from a velocity time graph, just read it off the graph. Is it all coming back to you, Austin? Nightmares of grade 11 physics? Number 4. Now, this is on the back side. Average acceleration. All of this stuff is exactly the same as what I just went through with average velocity over here. Okay? So, instantaneous or average acceleration, straight line graph. If it's a straight line graph and you want to find average acceleration, you find the slope between 2 points. Again, y2 minus y1 all over x2 minus x1. If it's a curved line graph, average means, Bailey says, over an interval. So that means 2 points. See how this is exactly the same as this? See, there, that, they're the same. And now in number 5, instantaneous acceleration. If it's a straight line graph, and you want to find instantaneous at a single point, how do you do that? Well, because it's straight, you can find the slope of the line, because the instantaneous slope remains the same throughout that slope, throughout that line, I should say. And if it's curvy, how do you find instantaneous at a single point? Connor? Tangent line. Pick 2 points, find the slope. Is that a lot to remember? Of course it is. But it's all right here. All right? I had a thought as I was going through that. I'll have to remember to do that. Remember how much fun the clickers were? We'll get a clicker. Hopefully I've got, actually, you know what, before I do that, as you're coming up, come and have a look at your number, because I can't make them any bigger. And if there's anyone up there, if there's someone in the room that isn't up there, let me know, because I can only add you before I start the class. I knew there was someone. You're going to be in non-alphabetical order, that's all. ALYSS double SA? Yes. Like that? Okay. Anyone else in the room that's not up on the list? Okay, so just jot down your number there. If you want to just put it on like maybe your course outline or something or other, something that is at the front of your book that's easy to find, because that's your number for the rest of the year. I will admit that I use these less than I do in grade 11. And I do apologize. The only way to make them bigger is to do this. I'll just kind of go down the list there. That's because I haven't turned it on yet. I wanted to make sure everyone was in. Everybody see their number? Okay. Yeah. Okay, you should be able to sign in now. Put in the number, yeah. Type in your number. 40 or 40. All of yours start with a 4 because of 40S. Okay. Austin, did you get logged in? Okay. All right, so it looks like everyone is in. So what I did was I created a sheet to go with it so that we're not having to wait for people to go. So take, I don't know, maybe 20 minutes, 25 minutes, I don't know. It'd be nice to get this done today. So the front page is a position time graph, and the back side is a velocity time graph. Okay, it's multiple choice. If you want to work with someone, that's fine, or a little tiny group, or whatever works for you. I'll check back with you at 9:45 and see if we're ready. Because all I got to do is press stop and you get ready. How's the lights over here? You guys need more light, or you can? Okay. just finish doing it. You guys close to done? It's okay if you're not. Just looking for some feedback. Martin, what number? Where are you? On the front side or the back side? Front side. Who's done the front side? Okay, that's okay. I wasn't trying to shame you, Martin. I'm just curious where people are. Do you want me to stop the front side? Oh no, you still working up, right? Okay, it's okay. If we have to give answers tomorrow, that's fine too. I'm not gonna say it has to come back to you. Okay. Okay. Come back to it. Okay. This is just sort of like the warm-up exercise to get you back. No? Okay, so remember you gotta find that you draw a line at the 0 mark. And you find where you're going from, 0 to 10. You gotta find all of the area, that triangle there. There's a rectangle all the way to there, I guess. And that little triangle right here. Yeah. It's from the graph to the axis. Yeah, you're gonna have to estimate there, I guess. How we doing here? That's true, yeah. Multiple choice. Sorry? Yeah. But it's only the area between the graph and the axis, so it's just that little guy there, and then over here, it's this one here. Right? It's not below, it's between the graph and the axis. Okay? Have you been entering your answers in the clickers as you go, or? Oh, because I didn't press start. Idiot.
Oh, I thought we were doing this.
No, that's me.
What?
That's me. Idiot. Oh, and I've been recording since the beginning.